Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the optical communication. Today in this video, we are going to talk in detail about the LED structure. So why I have different LED structure, why I am preferring a particular LED structure over another structure. For that you must understand the quantum efficiency and the LED power. I have already discussed the quantum efficiency and the LED power in the previous video. I hope all of you must have seen that video. If not, it is highly recommended for you to go back, watch it first and then come to this video. So let's start the discussion for today, that is the LED structure. Now I want as high quantum efficiency as possible. The efficiency or the quantum efficiency was related to the output optical power divided by the input electrical power. So I want the quantum efficiency to be as high as possible, and when it becomes high, the output optical energy or the output optical power will become high when the number of photons emitted by the LED are large. When the number of photons emitted by the LED will become large. When the total number of recombinations that are taking place inside the LED are large. When a lot of recombinations are happening inside the LED, a lot of photons will be emitted if all of these recombinations are radiative recombinations. So this is also a concern for us that the recombination should be the radiative recombination. Now when a lot of recombinations are radiative recombination, a lot of photons are emitted, and in this manner I can increase the optical output. So what I want high quantum efficiency. For that I want large number of recombination, which would be radiative recombination, and I want higher radiations. Radiations would be high only when the number of photons are high. So I want high quantum efficiency, high radiance and a fast response. The LED or the structure must be compatible to the input. So if the input has several changes which are very fast, then the LED must be providing the light in accordance to the input only. If the input is changing really fast, the light from the LED should also change really fast. I hope you understood it. So if I have a fast response, which means my processing speed or the data rate would be high, right? This is the requirement of the future. Okay, so I should have a LED structure which is giving me a high quantum efficiency, high radiance or low leakage current, or I can say a fast response. So this would be the ideal behavior of any LED, right? So now the radiance is measured in the output power per unit solid angle. Now the radiance is a 3D parameter. If I compute it, if I denote it similar to the light which is coming out from the torch. So if I want to measure the light which is coming out of the torch, so this is my torch and the light is coming out over here. So if I want to measure the radiance over here and the radiance over here, I need to have some 3D quantity. Only with the help of 3D quantity I can measure the radiance at different points. Or if I have two torches, I can measure and compare the radiance of these two torches with the help of the 3D angle, which is the solid angle. So solid angle is a very important parameter that is used to find what kind of radiation is coming out of the given LED structure, right? So now the geometry or the structure plays a very crucial role in determining the performance of the given LED. So different structures will be having different performances. So how I am measuring the performance? Based upon these three parameters, right? So I have 6 types of LED structures, but the basic 2 types are the planar LED and the dome LED. Now if I go in detail and if I see the most effective type of LEDs, it would be superluminescent LED and the resonant cavity or the quantum dot LED. So both of them are very effective, and this is the LEDs. If you have seen the LED inside your home, LED screen, so it is the LED which is giving me the 4K resolution. Right, so these are the best LEDs, but there is a problem with the best LEDs as well, that the price increase if I increase the quality of the LED. So there would always be a trade-off between the price and the quality of the LED. Right, so first discuss basic two types of LED which is mostly used in the optical communication system. With just some minor modifications, I can use both of them. So now if I choose the infrared version of planar or the dome shaped LED, I will be getting a high radiance LED. So I need to find out the infrared version. I can work upon the infrared version and I will be getting the best of the outputs. So both of them are economic, they are very cheap. Right, so they come in a very less cost and we all can use it in the basic applications. On the other hand, this superluminescent LED or the resonant cavity LED are comparatively more costly as compared to the planar and dome LED. Now, we all know as we increase the quality of the LED TVs, so its price is increasing. And now we understood it, that it is economical as well as it is rugged. Because this structure is a very simple structure, it is easy to fabricate as well. So now coming to the first type of LED structure, that is the planar LED. Right, we are going to talk about all of the 6 structures of the LED that we have. So now we have the planar LED. This is the structure that we have. We have the N type of substrate over which we have the P type of epitaxial layer. I hope you all have seen my VLSI technology playlist in which I told you how I can develop the layer of epitaxial region over the substrate. So I have N type doped substrate. Could be silicon or germanium or the gallium arsenide substrate, right? Over that we have P-type epitaxial layer which can be developed here or deposited here with the help of liquid or vapor phase epitaxy. Right? So here I will be making the ohmic contacts so that I can get the input current inside this structure and I can measure the output current as well. So I have to make the ohmic contacts over the P-type epitaxial layer as well as below the N-type substrate. Okay, so now you can see a significant portion of this P-type epitaxial layer is covered with the help of this ohmic contacts. So now the light can emit only at this portion and the total internal reflection will be happening. This is the junction that is formed in the N-type and the P-type region, which is the depletion region is formed around here. The total internal reflection will be happening and the light will emit through this region. But light is hindered by this ohmic contact at this region. Below the ohmic contact, light is not able to escape, and due to which the efficiency of the planar LED is reduced. Right, so it is the simplest structure that is available. I can simply make it or fabricate it by liquid or vapor phase epitaxial process over the full surface of gallium arsenide structure. Right, so I hope you understood this. So now Lambertian spontaneous emission will be taking place, and I told you in the Lambertian spontaneous emissions that light will be going in all of the directions. So after the total internal reflection, the light will be moving in all of the direction, but it is escaping through a low radiance window only. Okay, so we will be having the limited light which is escaping through the total internal reflection, which means I will be having the low radiance because of the less diameter of this window only, right? So its structure will be giving me low radiance. Now applications. This planar type of LED finds various applications like in the intruder alarms, the TV channel changers, and then in the industrial counting as well. Okay, for all of these things I can easily use the planar LED. Now coming to the dome shaped LED. So with the name, I can guess its structure is similar to the dome. Yes, the structure is like this. We have the p-type region over which we have the circularly shaped n-type region. It's a spherical structure that we have, and below the p-type region and the below n-type region we have the ohmic contacts. So you can see here we have the ohmic contacts below the structure, so the light can escape out in all of the directions. So it will be having better efficiency than the planar LED. This thing is sure. So it is having the hemisphere of n-type gallium arsenide which is formed around the p region. So I have a planar p region, but the n-type gallium arsenide which is formed is hemispherical structure. This is the reason it is called the dome shaped LED. Now if I increase the diameter, so I will be having the different properties and the decreased diameter. Now I want to increase the diameter to maximize the internal emissions which are reaching the surface within the critical angle of the gallium arsenide interface. So whenever I want to increase the emissions, I have to look for the diameter of the dome. The diameter of the dome is a very important parameter which tells me the emissions which are reaching to the surface. Okay, I will be having various emissions, but few of the emissions will be reaching to the surface and escaping the surface. These emissions are the desirable emissions, and these emissions are the emissions which I want. Now I am making the dome for larger than active recombination area. If I make the dome, then the recombination area would be much larger than the previous one. I told you if I increase the number of recombination, the number of photons will be increased. If I have the larger dome, the number of recombinations are going to increase, the number of photons are going to increase, radiation is going to increase. Okay, so I will be having the larger active recombination area. For that I will be having more recombination, more photons, and greater effective emission area and lower radiance. So I hope you understood the dome type of LED. Now we have one structure which is called double heterodyne LED structure. Now here you can see we have some ohmic contacts, and now here we have aluminium gallium arsenide structure which is p-type. Then we have the gallium arsenide structure which is again p-type. Now it is sandwiched with the n-type aluminium gallium arsenide structure. So we have two aluminium gallium arsenide structure in which the gallium arsenide structure is sandwiched. So now this structure is called the double heterodyne LED. I hope you understood this structure. Now this structure is very crucial to understand the other types of LED that we have. Then we have the surface emitter LED. What do you get from the name? That the LED is giving the photons from the surface. Right, this is true. So surface emitter LED is radiating from the surface. So this is how I will be having the surface emitter LED. Right. So now the radiance is improved here by preventing the absorptions. I am preventing the absorptions. Now here I have made a cavity, and due to this cavity I will be having lesser absorptions and more of the light is going here. Right. So the radiance is improved by preventing heavy absorption of the radiation, and the device is physically accommodated inside the fiber so that the coupling would be higher. Now what was the problem in both of them? You know, the light which was coming out was not very directional, so that the power which is coupled inside the optical fiber would be very less. So now here when the optical fiber is physically accommodated over here, so the coupling would be higher. So here what we are doing, as I told you, we are making a well inside the gallium arsenide structure. This is my n-type gallium arsenide structure, and this is my edged wall over there. And now here we will be having the active region over this region. Right, over the surface I will be having the active region. Okay, so here we will be having the metal tab, and now this is my edged wall, and this is the golden stud. And what are all of these things? So we have P plus gallium arsenide, This is the triple heterodyne structure. So P plus gallium arsenide, P type aluminium gallium arsenide, then P type of gallium arsenide. So if I see this structure, this is the double heterodyne structure, right? So N type aluminium gallium arsenide, P type gallium arsenide, P type aluminium gallium arsenide, right? So this structure is going to increase the recombination rate. So here a lot of electrons will be coming into the p-type gallium arsenide, and due to which it is going to increase the recombination rate, right? So here I will be having the low thermal impedance inside the active region. When the impedance is low, which means the hindrance is low, which means the power radiated would be high. So I will be having high radiance and high current density because of the low impedance. So double heterojunction is there. I told you here we have the double heterojunction. Double heterojunction is going to improve the characteristics. What all characteristics it is going to improve? It is going to get the less absorption. That is the need, right? For the surface emitter LED, the basic need was the heavy absorption should be reduced, and if I use a double heterojunction, the absorption will automatically reduce, which means it is going to perform better. So it will be having electrical and optical confinement as well. So I hope you understood the surface emitted LED. Now the edge emitter LED. As the name suggests, here we are having the emission from the edge only. So now which edge? The LED will be having two edges. Even these side edges would also be there. Upside downside surface would be there. I am calling them surface, so obviously upside and downside is ruled out. Now we have the four edges, and now in the edges I am radiating from only one edge, right? Other edges are mirrored so as to increase the stimulated radiation. So it is working upon principle of the laser. So it is having the injection type of structure, due to which I will be having the increased radiance. So it is having the transparent guidance layer. So the guidance layer is transparent, which is giving me very thin active layer, and which is around 50 to 100 micrometer only, right? Here you can see in this structure we have a stripe. You can see the length and the width 150 micrometer and 350 micrometer, and here we will be having the N-type gallium arsenide substrate, over which we have N-type gallium arsenide, epitaxial layer over which we have N-type aluminium gallium arsenide, P-type aluminium gallium arsenide, and P plus type aluminium gallium arsenide. What is P plus? Which means it is heavily doped, right? So edge emitter LED is also called DHE LED, means double heterodyne edge LED. We are preferring again the double heterodyne structure over here. So now it is working upon the principle of the laser. We know the laser is having the stimulated emission, and due to which it is having the highest radiated power. We are going to talk about lasers also in the upcoming videos. So as of now you must understand it is working upon the conventional laser principle, that is the injection type principle. So here we will be having the transparent guidance layer, thin active layer 50 to 100 micrometer long, due to which the self absorption is highly reduced, and that is what we want. I will be having the lesser divergence, and due to which the radiance is going to highly improve, and this is how I will be getting the edge emitter LED. So emit light from one face only because I have the reflector coating on the other face. I hope you understood the edge emitter LED. Then we have the superluminescent LEDs, which is used in most of the advanced application where cost is not a factor, right? So here we will be having increased output power. I will be having the decreased leakage current as well. So I will be having the directional output beam. The output beam is highly directional, which is giving me a best of the output, right? So I will be having narrow spectral line width, which means it is a good coupler. It is going to couple to the optical fiber in a very good manner, and which means it will be having low coupling losses. Okay, this is also very good advantage. Then we have the increased device modulation bandwidth. I want to work upon higher bandwidth so that I will be having higher data rate. So now coming to the basic principle, I told you it is working upon the laser injection principle, which is the stimulated emission. Now coming to the resonant cavity and the quantum dot LED. So it is also called RC LED. So it is again a very important type of LED which is used in the advanced application where again the cost is not an issue. So it is also called micro cavity LED, which is also called the mu cavity LED. So here we will be having a quantum well which is embedded inside the resonant cavity, and it will be having a planar structure. Okay, so the planar technology will be used to make the active resonant cavity. The resonant cavity is active in nature and it is in between the distributed Bragg reflector, which is called the DBRs, and which is used as a mirror. So the mirrors are going to increase the total internal reflected light coming in one direction only, and with this reason I will be having more intense radiation coming from one end. So the total internal reflection of a lot of photons will be happening, and a lot of photons will be simultaneously coming in a particular direction, and this is what is happening inside the laser as well, and this is the reason it is called, it is having the stimulated emissions, right? So now the cavity is amplifier to spontaneous emission and the reflectivity is maximum over here, right? The power is maximum over here. Okay, so the losses are least over here. So these are the various advantages. The efficiency would be very high in the case of RC LED. So I hope you understood all of the things that I have discussed in this video. If you have any doubt, you can put the doubt in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button. Subscribe to the channel, share it with your friends and give me your feedback. Thank you so much.